Oh, it's recording. All right. So today we're going to be going over exploratory factor analysis or EFA. One of the two. Can't decide. You get to choose. So normal setup procedures. We're going to do library read Excel, library corp core, library GPA rotation, and library psych. Just loading all your libraries in and loading the data set. We're going to do that in the classic fashion. And we're going to want to get rid of any missing data because EFA literally will crap itself if you have missing data. It just doesn't like it. So getting rid of it using the NA omit in your data set. Next, you want to create a correlation matrix for the data. EFA runs off of this correlation matrix. So it needs to be able to see that your factors are correlated. But you don't want them to all be the same factor, and you don't want them to not be correlated at all. So you need that happy medium, and so you would test that through core test Bartlett, which is basically the Bartlett test, which tells you that the matrix is not an identity matrix if it is significant. So we want it to be significant, implying that there's relationships between the variables, but that they're not the exact same. So the next section, the lines 19 through 50, is the building of the KMO function, and that is the Kaiser-Meyer-Olkin criteria. I think that's what it's called. But basically, it is a function that someone made in order to do the KMO test of common variance. And it's not a package for R, so you have to pretty much run this in order to get the degree of common variance and how acceptable it is. It's an assumption for EFA that is basically how much common variance is present in your data set. And basically you want, it scales it from 0 to 1, and you want as much as possible. So it gives these neat little rankings of marvelous, meritorious, middling, mediocre, miserable, and unacceptable. So it basically tells you how good your sample size is and if you're ready to go for factor analysis. So you would create this function using these fun little, I honestly don't know what all of this does. I found it in the, who wrote this? Field Miles and Field 2013, Discovering Statistics Using R book. They have a bunch of stuff on their website, so that's where this is from. But the KMO, you run that using your data, and it tells us if the data and sample size are good to go based on the merit. So you can actually start looking at output, sorry. So the correlation test, the Bartlett, using the EFA matrix. So it's a chi-square test, and so it gives you your p-value and your degrees of freedom and your chi-squared value, and you want to report all of these in an output. The KMO function, so it tells you the overall, and then it also prints the report. So it tells you that for my data set, it has yields a degree of common variance is meritorious. So it has that 0.89. So it's in this section here. So it's good data. It's good to use. Next, we want the determinant of our correlation matrix, which is the third assumption, and it basically tells us if we have a multicollinearity problem. But this section down here is from the KMO, and it's basically looking at all the common variance between the items. And because we had 28 items, it looks at the correlations between all of them. So there's a lot of output here. It looks at the different AIS and AIR. So the determinant, we run that. If it is smaller than 0.001, we may have multicollinearity problem. We do. for this. It is so small. It's actually only, I think, 1 or 2 decimal points, or 1 or 2 zeros away. So we do have a multicollinearity problem, but if your KMO is good enough, it kind of overrides this. It's like when you have non-normal data, but you know your other assumptions are met, and you're kind of like, we'll be fine. So next is the actual running of the EFA. So the running of it uses the factor analysis, and you want to use the correlation matrix that you made before and tell it how many factors are in your data set. And the original one, you don't want to rotate it. You only have to rotate it if your data's fucky. So you want to run one factor analysis without rotating it. And because my data is multivariate, I'm going to use the multiple likelihood factoring method. So this gives us all of this information. We have the standardized loading patterns, which basically shows us where each of the items, which are these, the columns, load on. The MLs are each of the factors. So this item loads highly on this factor and not really on too many of the other ones. So it basically builds a matrix of the item loadings. It also gives us these two things, H2 and U2. H2 are the commonalities within the items, and U2 is the specificity within the items. And basically those are used, excuse me, as, commonalities, and U2 is the uniqueness. So the commonalities are important because we want an average above 0.5. And that's just another assumption in the data. So if our average is below 0.5, so you would look at all of these, our average is above 0.5. If our average is below 0.5, but our sample size, with a sample size of less than 500, our data may not be adequate enough to yield distinct factors, which happens. So you can either go collect more data or make sure that your KMO test says that you're good to go. So the KMO pretty much overrides this. So we can continue with our analysis. This is particularly important, the SS loadings. This is basically the eigenvalues for your data. So basically, Kaiser from 1974 in his paper says that values over 1 indicate good factor loading. So there's a lot of loadings onto 1, 2, 3, and 4 factors. So there may be 4 factors present in this data, but there are other ways to check. For example, a scree plot. The eigenvalues are basically the proportion of the the proportion of the variable, how much total variance is explained by the item, by each item, yeah. So now, the proportion variance tells you the proportion of the variance is explained by how much, proportion variable is what percent of the variance is explained by that factor. So factor 1 explains 31% of the variance, and that pretty much just goes through the rest of them. It's not going to add up to 100%. So the next portion, wow, is plotting the scree plot. Where's my scree plot? Ah, I shrunk it. That's why. So this section over here plots the scree plot, which personally I hate. This one's actually kind of decent. It is a way to retain factors, essentially. So where a bend occurs, essentially, is kind of where you will be retaining factors from. Anything that where it starts flattening out, you can kind of put the cutoff in between there. So the cutoff could be right in between 4 and 5, or it could be in between 3 and 4. And just for the sake of showing you, I'm going to run both of them. So I'm going to show you the differences that appear in the data when you run both of them. So back to the syntax. We're going to run the same command as we did up here, but we're going to specify that there are 4 factors, and we're going to use the oblim rotate, which is an oblique rotation because we expect the factors to be related to each other. So that is this portion down here, and everything is pretty much the same in terms of output content, but you will see that it's not super far over here because we specified that we only wanted the 4 factors, and it still shows us the communalities and the uniquenesses. And you'll see that the eigenvalues have actually increased. So we have 5, 3.29, 2.49, and 2.07 versus the 8.58, 2.23, 1.1, and 1.108. So they've pretty much gotten redistributed, essentially. So we can look at the section right here, the print psych, will give us an output that shows us where the items load onto what factors. So it's a way to group them together. So I'm going to get a little more real estate here. So that's this section right here. So each of these is the item, and each of these is the factor that they load onto. Now, I believe that it was Stevens, 1972, that says you would focus on factor loadings greater than 0.4. So all of these would potentially be one factor. All of these would be a second one. These would be a third. And these would be a fourth. However, you notice there are a couple of them that have factor loadings on more than one factor. This is basically cross-loading, and essentially when this occurs, depending on the number, not the number of factors that they load on, but depending on the output value, Tabachnik and Fidel suggest that if it's over 0.32, you may want to just throw that item out. It may be a bad item, but if there are factors that have strong factor loading, so like this 0.5, it's still a good factor, but some of the other items may be trash and you have to throw them out or reword them. They may be poorly worded. So that is how the items load onto the different factors when we have 4 factors. And I wish I could do a side-by-side comparison of what happens when we run them with 3. Actually, I can. Just give me 1 second. So getting back to the syntax, We're going to run the same thing, but with 3 factors. It's pretty much the exact same with the print psych. And so on the left side will be the 3 factors, and on the right we can compare it to the 4 factors. So this is what happens when you specify 3 factors. And shrinky dink that. Nope. I want it side by side. So here are the ones from when we specified 4 factors, and here are the ones from when we specified 3. And as you can see, some of the items disappeared, some of the items loaded differently, and some of them are loading lighter or heavier. So like question 22, for example, question 22 originally loaded on factor 1 while it didn't load, while it loaded more heavily on factor 1 again, but with a different weight. So it's 0.63 here. Oh darn, everything's ruined. So it's 0.63 here, but when we had it on 4 factors, it was 0.84, and it wasn't cross-loaded with anything. So depending on the number of factors you decide to retain, it may change your factor loadings. So based on this, this is how you run an EFA in R. And the interpretation of this will be in the paper. Bye.